Okay, so we understood how to how to convert text into numbers. Basic approach. Basic approach in the sense bag of words approach. I am saying basic approach. That doesn't mean it's the simplest one or smallest one. Depending on the situation, this also may be useful. Right? I gave you one example, right? So if you are trying to distinguish between bank forms, right? Classify different bank forms. The text is going to be common, and you need to, by looking at the count of different attributes, you will be able to distinguish one document from the other. So count of the strings or the text words in the document is actually distinguishing. So count is important there. In that case, you need to take bag of words as an approach to convert text into numbers.
Okay, sir, are you sharing the screen, sir?
Oh, sorry. But nothing I am showing right now, but so that's the example I have taken for bag of words to work. Right. So we need to look into the theory behind naive Bayes algorithm. We looked into naive Bayes algorithm, right? So we are going to cover one more algorithm, which is naive Bayes algorithm. And in text problems, naive Bayes is used. I'll explain why in a moment. So it's a probabilistic algorithm. We are going to learn some probability theory, about some probability here. This may be used in NLP a lot. Okay. The So Bayes theorem is the basis for this naive Bayes algorithm. We call it as naive because it assumes that all the input features are independent. Okay, around this, the whole discussion will happen. All the input variables are independent. That's where we call it as naive. And Bayes algorithm, it is based on Bayes theorem in probability. The goal is to predict y. Right? Whenever we get a data set like this, whenever we get a train set, the goal is to get a new record. When you get a new record, you need to predict the y variable. That's the goal. Right? So given x, right? So the point is like the goal is to predict y given x. Right? This is represented like this, y given x. We already saw this before, right? You remember. So when I say y given x, sunny, hot, high, weak, that is all x. Right? Do you agree with my statement? Sunny, hot, high, weak. That's one combination of x. Do you agree? Hello?
Yes, yes.
Right? So when I say y given x, right? Probability of no given sunny, hot, high, weak is what? How much? Can you calculate? Probability of no given sunny, hot, high, weak. How much?
So
So we need to
probability is
calculate
1/4, right? Sunny.
No. Let me write it down. I am saying
we,
4. Huh?
yeah, we need to calculate probability of each one and multiply. Probability of sunny is 1 by 14. Temperature all 1 by 14 I will do, right?
Yeah, 1 by 14 it is, right? It's a combination I was actually talking about. Okay. So I'm actually asking like, probability of no given, all, sunny, hot, high, and weak. Right? All these four variables, x1 is equal to something, x2 is equal to something, x3 is equal to something, and x4 is equal to something. Okay. So this is equal to 1 by 14. Out of all the combinations, all the test records, only once it is out of 14, it is only one combination. This particular thing will happen only once. If I ask you probability of yes given, same combination, sunny, hot, high, week, the same record. This particular X, getting yes, if you pass this particular value is how much? Do you have the same combination?
It should be 0.
0 by 14, right? It is 0. Getting it? It is just the count, right? It's just the count, right? How many times no when this combination is present? This particular combination is present in the train set. How many times it is no? Right? This is the problem. When this is the problem. When you get the same combination, you will be able to predict it. If the new combination came, right? Maybe like rain. I think we had one example, right? I think rain, maybe mild, cool, rain and mild is there. Rain and hot is not there, right? Rain, hot, high, weak. This may not happen, right? In reality, this may not happen. If I have to predict the probability of yes, they'll play, right? When rain, hot, high, weak. Can I predict this one? Can I predict this one? Can I predict this one?
If the combination is not there, we cannot predict.
Yeah, it is 0. This one is also 0. This one is also 0. Right? Most probably they'll not. We don't know whether they play or not play. Right? So this is the problem. With the probability, this is the problem. That's where we take independence assumption. When you take independence assumption, right, some flexibility will come in calculating probabilities. So that is naive Bayes algorithm. So there is a problem in calculating probabilities when the combination is not present in the train set. To solve that, there is an assumption, independent assumption that gives you a little flexibility to calculate probabilities. So statistics is all about estimation. It is not about accuracy, right? Can you do it perfectly? That's not the question of statistics. Can you do it or not? That's the question. Statistics will answer. Okay, we call this algorithm naive because the algorithm assumes independence. What will you get when you assume independence? I'll talk about that. Basic naive Bayes theorem is probability of y given x can be calculated by calculating probability of x given y into probability of y divided by probability of x. Okay, this is called a conditional probability. If we have to calculate this, right, whatever I wrote was a little layman's kind of a thing. Right? If you have to calculate, probability of yes given, sunny, hot, high, weak. Sunny, hot, high, weak. Sunny, hot, high, weak. Right? If you have to calculate this, right, you should be using this formula to calculate it. So this formula is like probability of x given y. X given y means sunny, hot, high, weak given yes into probability of yes, right, divided by probability of how many times, right, this sunny, hot, high, weak is happening. Right? This is the formula you need to use to calculate the actual probability. Okay, previously I was talking as a layman, right? So if you have to calculate this, right, so how many times this is yes when this combination is there, that count will come. How many X's are there, right? Out of 14, 9 X's are there, right? 9 by 14 and divided by how many these combinations are there. You need to use that. So if a new combination comes, right, you cannot actually find out this particular probability. So to do that, we are doing a independence assumption. So the probability of occurrence of event changes when one or more conditions satisfy. Right? Probability of y given x is denoted as this, and the machine learning perspective, right? The probability of y given x, the probability is calculated using data present in the train set. So if the train set is taken, the sample is taken appropriately, you will be able to calculate probabilities appropriately. So basic machine learning approach is that it uses train set and tries to calculate probabilities. So what is independence assumption? I'll explain in a moment. Okay, I think I took a simple example and tried to explain this. So here I have taken a simple data set, right? X1, only one column, and Y. Okay, and then I am, if you have to uh, predict whether a record belongs to, if A comes, right? What is the is it belonging to 0 or 1? We need to predict. To do that, what we can do is we can predict probability of 1 given x1 and probability of 0 given x1. Whichever is high, we say the record belongs to that particular class. Okay, we need to predict this class, this record, which class it belongs to. How naive Bayes algorithm does it, or probabilistic approach does it? We calculate positive probability, negative probability. If positive greater than negative, we say record belongs to 1. Otherwise, we say the record belongs to 0. That's how the naive Bayes algorithm predicts. Final approach, you got it, right? Any questions here?
Yes, sir. So when we say positive, negative, it's only classification problem? That's it?
Yeah, classification only. Naive Bayes algorithm is useful for classification only. No regression.
Okay.
Sir, what is the major difference between decision tree and the naive Bayes, sir?
Decision tree is based on condition, right? It actually splits data based on condition.
Yes, sir. Formula is different, the way is different, but finally, like, which one is better to use, sir? The data is same, right? Data set same for the decision tree or naive Bayes, right, sir? So how do you choose that, whether we go for decision tree or naive Bayes?
See, decision trees are more complex in nature when compared to naive Bayes algorithm.
Okay,
Naive
okay.
Bayes is a statistical approach. Decision
Hmm.
tree is the logical approach. And when you use random forest or bagging or boosting algorithms, right, it will become very powerful because it actually goes through all combinations and tries to find best way to split and make prediction, right? It's
Okay.
actually trying to, it is like a British rule, divide and rule. Right? It is actually trying to divide and dissect everything and open it and show. But here it is not happening. It is not dissecting. It is just trying to calculate probability. I'll
Okay.
talk about it at the end, right? I'll talk about where exactly the naive Bayes algorithm is useful. I have taken the same data set because it's easy to explain.
Yes, sir.
It's easy to explain. Right? So here, we need to calculate probability of y is equal to 1 given a and probability of y is equal to 0 given a, because the new record, the x is a, right? X is a, y which record, which class it belongs to, we need to predict. So to calculate the probability of y is equal to 1 given a, right? This one, probability of y given x, right? We are trying to calculate. I am using naive Bayes algorithm. Probability of x1 is equal to a given y is equal to 1. How many are there? This one and this one, right? X1 is equal to a, where y is equal to 1. Out of 5, what are 5? A's are 5, right? 1, 2, no. Give me one second. Yeah, ones are 5. 1, 2, 3, 4, 5. Right? Till here, that is training set. Okay, we should look at that part only. We shouldn't look at this one. Okay, this is actually the new record which we are trying to predict. So out of 5 ones, 2 ones belong to A. Okay, So if you are saying probability of A given 1, you need to look at the y counts in the denominator, right? In the previous example, right? Where is that? This one. See, this I said, the 14, right? 14, 1 by 14. Actually, I should be counting these combinations, right? These combinations on the denominator. When I'm saying we cannot calculate this, actually. Sorry. So only when the naive base is there. Sorry, give me 1 second. I am getting confused. 2 by 5. So in that case, we actually need to say, right, this, yeah, this we cannot calculate actually. Divided by 1, we'll get, right? So if you try to use the same conditional probability formula, right, it is not 1 by 14. Do you agree? Denominator is going to be 1, right? The combination is not repeating, right? 1 by 1 it is, and it is 0 by 0 or 1 by 0. It is undefined. Got it?
Sir, for which case you are saying, sir?
Sorry, I am confused and I am confusing you. Sorry for that. If you look at this, right, probability of 1 given A we are trying to calculate using naive Bayes algorithm, right? So here probability of 1 given A cannot be directly calculated. So we are using the naive Bayes algorithm. In that we are using a conditional probability here. Right? Probability of A given 1 we are calculating, right? This one I calculated here. Right? I said 2 by 5. Right? How did I say? This 2 by 5, how did I say?
We took all the records with y equal to 1. That is the denominator.
Yes, sir.
In that, wherever
we took all the numerators, wherever that on the x side, wherever it is A, we took that with 1, and that is numerator, right?
Yeah.
Right? That is conditional probability. Okay. So if you have to, if you have to calculate this directly, you cannot calculate. That's what I'm trying to say. You can, if you want to calculate this directly. So I tried to do that here. See this here? I actually tried to do this. No given all, S given all. Right? S given all, no given all. I tried to directly calculate it. We cannot calculate. That's what I'm trying to come back and say. Leave it. Okay. So here probability of 1 given A can be calculated using this, and this probability how I calculated, you got it right. It's a conditional probability. We call it as. This part you got it right.
Yes, sir.
And probability of y is equal to 1, this you know already. How many records are there? Out of which how many ones are there? Right? 5 ones are there. Okay, I calculated that, I substituted that into formula. Numerator I am calculating, denominator I am not calculating. There is a reason. Okay, numerator is 0.25. Right? Probability of y is equal to 0 when x is equal to a. This I need to calculate. To calculate that, again conditional probability. Probability of a given 0. Right? How many a's are there when it is 0? Only 1. Right? Out of 3 zeros, this is 0, this is 0, and this is 0. Out of 3 zeros, only one is, right, 1 by 3. Right? What is the probability of y is equal to 0? It is 3 by 8. So I substituted that also. I have got some numerator. If you look at this formula and this formula and the end result, denominator is same, right? Whether we calculate it or not, it doesn't matter. If you look at these two, which one is high? Probability of 1 given A or 0 given A? 1 given A or 0 given A?
1 given A.
1 given A. Do we need to calculate denominator?
Not required, sir.
Not required. Just to predict, denominator is not required. That's where even in naive Bayes algorithm we will not calculate. It is just the Bayes theorem. I have taken a simple example and trying to calculate probabilities of positive and negative probabilities using Bayes theorem. Okay, here the record belongs to 1 because the probability of 1 given x is high than probability of 0 given x. Okay, so if you have two input variables, what is the problem? If you use Bayes theorem, what problem we will get? Why do you need to take independence assumption, and why do you need to why do you need naive Bayes algorithm? That's the question I am trying to answer. So this is Bayes theorem, not naive Bayes. This is just Bayes theorem. I have taken two input variables, x1 and x2. So I am trying to calculate probability of 1 given c comma b, right? X1 is equal to c and x2 is equal to b. To calculate this, probability of x1 is equal to c, x2 is equal to b given 1, we need to calculate. So do we have a b and c combination in our data set? Do we have in our train set, do we have b and c combination? Anywhere?
No.
No, right? So, and again for 0 also same thing. So you will not be able to calculate the probability if a new record comes in with the combination that is not present in the data set, you cannot calculate it. Okay, this is what I was actually trying to go back and forth. So if the combination is there, you will be able to calculate this. Right? How many ones are there related to that combination? How many zeros are there related to that combination? You can calculate as we did before. Here, right? If the combination is not present, you will not be able to calculate the probabilities. You will not be able to predict. This is where you need to assume independence. Right? When I say independent, right, there is no relationship between x1 and x2. In real time, in any data set, not real time, in any data set, there will be some relationship, a little bit of relationship between the input features. And some features are maybe, multi-collinear also. Okay, but naive Bayes algorithm assumes it because there is no way that you can calculate probability for the combination that is not present in the training set. Now, I think Narayana was actually trying to point out the same way, right? Even in the tree-based algorithms, when the combination is not present, we will not be able to predict, or we may predict, that may not be right, right? So what we are doing, we are actually taking subsets of it and then trying to build many trees and making decisions and trying to take, the ultimate, the combination of all those results, right? So, like that here also, we are trying to find out a way to predict the outcome, because there is no way that you can calculate probabilities when the combination is not present in the train set. Okay, so naive Bayes algorithm. Now, the independence assumption. If you assume that the input variables are independent, you can calculate the probability of this particular part, right? Probability of x1, x2, and so on, xn given y can be calculated like this. Probability of x1 given y, probability of x2 given y, independently you can calculate and multiply. I think Seshiram was actually trying to say we need to multiply the probability, right? This one, right? This is the one, right? You are saying in the beginning, sir?
Yes, sir.
So when you assume that all these input variables are independent, then you can calculate individual conditional probabilities and multiply them to generate this conditional probability. Okay, this is the independence assumption. Why we are assuming this? If this whole combination is not present, there may be individual, probabilities present. Individual means there may be x1 with y, x2 with y, x3 with y, like that. May not be total combination present. Individual ones may be present. So we'll be able to calculate some probability. This is where we call it as the algorithm naive, because even though there is relationship, the algorithm is assuming that there is no relationship. That's a naive assumption. Naive means innocent. Okay, innocent assumption. So naive Bayes algorithm uses Bayes theorem. The goal is to predict y at whatever means we are going to predict y. Right? The target variable with k classes, the target variable with k classes, yk I said, right? So it can be yes, no, 2 classes, right? Yes, no, all right, 3 classes, right? Given x, set of x1 and so on xn, for n input features, we call this algorithm naive as the algorithm assumes that all these are independent, because if you don't assume independent, you may get stuck with this kind of a problem. When the combination, when a new records combination is not present, you will not be able to predict. Okay, so for that we are assuming that when you assume that, this term becomes free like this, and you will be able to calculate. Okay, I'll show you the example also. No need to compute denominator. We already seen that. As we compare the probabilities for different classes k, right? We actually did here. We compared probabilities of 1 given a and 0 given a. Whichever is high, we are predicting the record belongs to that class. So no need to calculate denominator, right? Whatever theoretically is written is already shown there. Okay. So there are two, terminology here. We need to remember this, right? Terminology: prior probabilities and posterior probability. So what we need to predict, right? One, yes given the record or no given the record, is the posterior probability. Okay, what we are going to find out ultimately is called as posterior probability. There is prior probabilities. So prior probabilities are probability of, some feature given yes, some feature given no is already there. Okay, we can calculate that. Probability of yk is also already there, because on the y variable, probability of 0 is 3 by 8, probability of 1 is 5 by 8. Right? Probability of yk is already there. Probability of x given b, right? Probability of x1 is equal to a given 1 can be calculated. Probability of x1 given x1 is equal to b given 1 can be calculated. Probability of x1 is equal to c given 1 can be calculated. Probability of x1 is equal to 1 given 0 can be calculated. That's all counts. Those are all counts. Right? Combination may not be present, but individual, columns and the values may be present. Now we are going to do naive Bayes. Right? So with independence assumption, the Bayes theorem with independence assumption. So I have taken the data. Right? Now I am trying to predict which which class this record belongs to. Right? Which class this record belongs to. Probability of y is equal to 1 given x1 is equal to c and x2 is equal to b. So that can be, that can be this probability. Right? Probability of c comma b given 1, that combination is not there, but we are assuming independence, so we can calculate that like this: probability of x1 is equal to c given 1 into probability of x2 is equal to b given 1. Right? Probability of x1 is equal to c given 1. How many times there is c with 1? Right? There is 1 here. There is 1 here. Two c's are there with 1. Right? 2 by 1. Y is equal to 1 is 5 times. Out of which c is equal to c belongs to 1 is 2. Right? Getting it, right? This part 2 by 5 is what is the one we calculated. Right? This part. And this part is 1 by 5. There is b and there is 1. Only once b is equal to 1 in x1. Got it? So because of the independence assumption, we were able to calculate this numerator probability. So this is the probability, and p is equal to 1 is probability of y is equal to 1 is equal to 1 is 5 by 8. Right? We multiplied these two numbers, this part and this part, we got this. And again we calculated the same thing, this part at 0 thing, and then multiplied, we got. And if you look at this, the positive, the y is equal to 1 is greater than y is equal to 0. Hence the record belongs to 1. it's a very marginal difference, right? So this is how the naive Bayes theorem internally calculates the probabilities. Any questions? And independence assumption is needed because all the combinations in the production may not be present in the train set. Ensemble, right? The what you call it is random forest or bagging algorithms are also doing the same thing, right? Even when the combination is not present in the train set, it is taking subsets of it and trying to calculate. Like that here also, it is taking sets and independence assumption here. It is not, we shouldn't be saying subsets. There is some similarity as Narayana was trying to say. But any questions, Andy? Any questions? Are we good? Are you guys there?
Yeah, understood, but is it accurate or is it going
No,
to
it is
be?
not going to be accurate. No, it's that's prediction, right? When you say prediction, right? Never you get 100%. Okay, is it going to work better than other algorithms? Maybe, may not be. We'll talk about that in a moment. So when to use this algorithm? That's the question, right? In a way.
Yeah, kind of, yes.
Yeah, in a way. Yeah. So I try to dismantle this as much as possible. So there are other problems also. We'll talk about them in a moment. So I'm trying to take that whole theory, whatever written there is here also. I try to take the same data set, for the tree-based algorithm, the same data set I have taken here, and I'm trying to predict for these two rows. Right? There is a concept called as frequency tables and contingency tables, likelihood tables. Sorry, likelihood tables. So what is this kind of frequency table? In Outlook feature, how many sunnies are there, right? Which are belonging to yes, which are belonging to no. In Outlook column, how many overcast are there? How many belong to yes? How many belong to no? Right? How in our Outlook column, how many? So when you actually use naive Bayes algorithm, it finds out these frequency tables. Using these frequency tables, it will calculate likelihood tables, the probabilities. Okay, and then these probabilities, independent probabilities, right? So x1 is equal to, you need to calculate probability of S given, outlook is equal to sunny, temperature is equal to cool, humidity is equal to normal, and wind is equal to weak. If you have to find out that probability, right? We are assuming that the outlook, temperature, humidity, and wind are independent. Are they really independent? In reality, if you talk about weather, the outlook, temperature, humidity, and wind are independent?
No, sir.
No.
In this particular data set, you should not be using naive Bayes algorithm. Right? Got what I'm saying? On this data set, you should not be using naive Bayes algorithm. Why are you using it? It's a small data set, simple to show. Okay. It is very simple to show you the problems in the algorithm and how it is working and all that. If you already know that the data set has got strong dependency between input variables, you should not be using naive Bayes algorithm. If you want to still desperately use naive Bayes algorithm, is there any way? Do we know a way to make the input variables independent? Do we have a way? If you apply PCA, what happens? If you apply PCA, what happens to the input variables?
Yeah, they will become independent.
They will become independent, but is there a problem there? If you know, will it work? You know, I am saying the question is like this. You know, when you ask when to use an algorithm, the question is like this. In our data, are the input variables dependent on each other or not? That's the first question. If they are dependent, I still want to use naive Bayes algorithm. So can we make input variables independent? Yes, by using PCA algorithm, you can make input variables independent. But when you make the input variables independent by applying PCA algorithm, is there a guarantee that the algorithm works on the PCA transformed data? When it works, when it will not work. When you apply PCA, two things will happen. One, they'll become independent. Two, the columns will represent the correlation, the relationship between the input variables, right? Right? Do you agree with my two statements? Should I repeat?
Yes, yes.
Anybody, do you want me to repeat?
Yes, sir. Please repeat.
So when you apply PCA on input variables, I'm saying input variables only because it's an unsupervised learning technique. When you apply PCA on input variables, the outcome becomes independent. The columns become independent. But it is going to extract the essence of the data, right? Essence, what is the essence? It is going to extract covariance or the correlation, right? So if the correlation, right, if the correlation, the strongly correlated features are the ones which are actually having highest predictive power, the PCA transformed data you apply naive Bayes, the algorithm works fine. If the strongly correlated features are not the ones who are having strong predictive power, then it will not work. Even if you make the features independent, even then it is not going to work. Okay. So the point I am trying to make is the basic assumption of the algorithm, if the data is satisfying, then you can use it. If the basic assumption the data is not satisfying, you cannot use it. In this particular scenario, weather, right? One is dependent on other. When raining, there may be wind and it is going to be cold. Right? When it is sunny, there may be wind, but it is hot. Right? These are all input variables which are dependent on each other. I should not be using naive Bayes algorithm, but I am using it because the data set is small and I am trying to explain that. When will we get a data set which is completely independent? Never. But if you look at this, if you look at this data and the way we converted that into numerical form, will there be a strong relationship between the input variables? When you do count vectorizer, will there be a strong correlation or weak correlation between features, input features? On a text data, when you converted it into a count vectorizer, between columns, what are the columns here in the count vectorizer? What is this first column? What is the first column?
First word.
First word, second word, third word, fourth word, fifth word. From where those words are getting?
Input
Total
data.
data. Total data, right? All the reviews. Is there a guarantee that all these input variables are strongly related or weakly related? Anything?
Before converting into numerical,
Ah,
we can't say, but after converting into numerical, I'm not sure. Before converting into numerical, we can say there may not be strong relation.
See, when somebody is writing a review, your language may be different. My the language means English may be same, but the way we express may be different. I may say, I love the food, I love the place, but you may say, I like the food, or the dosa is very good, or maybe idli. So every review will have mostly I am not saying always, mostly the words will be different, but the expression may be same, right? When the words are different and expression is same, you will get different columns there, and there may not be, there may not be much strength or much, correlation between the features, right? On a text data, you can apply naive Bayes algorithm because there may not be that strength, that much strength. There will be relation, right? Love and like are having relation, and they actually have positive feedback, positive y variable. But if you look at a high level, right, it's okay. It is not like, when it is raining, it is going to be cold. It's very strong, right? And there is going to be wind, right? And when it is sunny, it is going to be hot. There is no other way. Sunny and hot are going to be there always. It is very strong there. But here it is not that strong. And especially when you actually create, like, and there are around 1500 columns here. When you actually did count vectorizer with all the features, right? Max features, you don't, when I did not give, there are around 1500 columns. When there are that many columns, right, definitely there is not going to be that much strength. Got it? Got it? Any concerns, questions? No? Guys, got it? Can I move on?
Sir, I have one question, sir. Here, max feature you are taking the 20, sir. Sir, is there any way to do some cross validation to find out the best one,
That is
best max
again
feature?
hyperparameter, sir. We need to change it.
Hyperparameter, we can.
We need to change it. It's a trial and error. We need to change it. And when you look at the data, right, you will get that understanding. When you do data analysis, I'll show you how to do data analysis on a text data. We'll do frequency counts and all, right? Maybe Monday I'll show you, right? So when you do that analysis, right, you will get a little bit of idea. It is not going to, you are not going to get everything, but you will get a high level picture on how many features I can choose and things like that. It is all, data scientist's effort that actually makes the model work. I think by now you got it, right?
Okay.
So this point you got it, right? When you have too many features, there may not be, right? If this data set is small. When you take text data, you will get a minimum 10,000 columns, minimum 10,000 features, minimum 10,000 distinct words. In that case, you can apply naive Bayes because there is independence in the input. You can use naive Bayes. Okay, got it?
Yes, sir.
So Seshiram garu, now you can say that this algorithm works on some data sets, right?
Yes, sir.
So that's how you need to choose the algorithm. Depending on algorithm strengths and weaknesses, we need to see whether the same things are present in the data or not. If both are matching, then we can use the algorithm and it works. So you look at these frequency tables and look at the, sorry.
So here also, like this weather data, these input features are strongly related to each other.
Yeah.
And these input strongly related features are actually deciding the output variable.
Yes. Sir.
So can we apply PCA and use naive Bayes?
Yeah, we can. Then it will work.
Okay.
And work better. I think it should give more, clear predictive power, and yeah, it should work better than whatever we are doing now.
Okay. Okay.
So when the features are not independent and you are trying to assume independence, right, you are actually destroying some strength in there, right? So when you apply PCA, it should work better. Yeah. So we are taking counts here, right? How many outlooks sunny yes belong to yes? How many sunnies belong to no? How many overcast belong to yes? How many overcast belongs to no? This zero is very important. I am actually trying to come here and go back because this part is very important. Look at it, and I'll point out in a moment. Okay. So I am calculating this. Okay. To calculate, if you look at this y given input. Yeah. So to calculate that, I need to calculate, this is the naive Bayes algorithm. Probability of sunny given as into probability of temperature given as individual variables given y variable. Individual variable given y variable. Individual variable given y variable. I am multiplying them into probability of x. Denominator I am not going to calculate. Numerator I calculated. Even on the no case also, right? Same combination of x. What is the probability of belonging to S? What is the probability of belonging to no? Right? If I look at the numerators, S is higher than no. Right? For no, it is actually 0.003. For S, it is 0.017. So the record belongs to S. Okay, that's how I predicted. Okay, this far it is good. But there is one point I wanted to explain. If the outlook is equal to overcast, if outlook is equal to, instead of sunny, if this is overcast, what happens to this probability? If outlook is equal to, let me take a screenshot and try to write. Maybe that is okay. So if this one, right, overcast. What happens to this probability? Or here also overcast. Right? This probability and this probability. What happens?
Numerator, the first one is 4/9 and the second one is 0/5.
Right? This becomes 4/9. This becomes 0/5. What happened to second probability?
0.
This whole thing became 0. Right? This is a problem. So to solve this problem, right, there is a concept called as Laplacian correction. First thing, right, when we actually we are using naive assumption because the total combination may not be present in the data, right? Even when we divided the data into independent assumption and then we divided the probabilities and multiplying, right? Splitted the probabilities and multiplying, we have the zero probability problem. The zero probability problem, right? To avoid the zero probability problem, there is a concept called as Laplacian correction. What we will do is, for every numerator and denominator, we'll add one. Here one, here one, here one, here one. Is that correct? No. But statistics is all about approximation. So these probabilities will become, if you apply Laplacian correction, right, this becomes 3/10, becomes 3/10, this becomes 4/6, this becomes 5/10, this becomes 1/5, this becomes 4/10, this becomes 3/10, 3/6, right, 1/6, this is, right. So after applying Laplacian correction, we will not get zero probability here. 1/6 we will get here. These are all sixes. These are all 4, 2, 2, 6, 6, 3, 6. Right? This is going to be 6/15. Okay. Why are we applying Laplacian correction? Because of one probability becoming zero, the total is becoming zero. Even though there is some strength to other features, right? Because of one feature or one attribute of a feature, the total probability is becoming zero, right? The predictive power is getting reduced, right? Maybe the record belongs to zero. Because of this zero thing, the total thing may have become zero. So Laplacian correction is one technique which is going to save us from zero probability on belonging to yes or no. Did you get it? What is Laplacian correction? Did you get it?
Yes, sir. But in order to impact the accuracy, this concept can be applied only
Yes.
when there are lots of combinations. Then accuracy may not be compromised that much. Otherwise, it will be compromised a lot.
Yes, and yes. And we don't know, right? In some cases, there may be zero probability. So applying Laplacian correction is not going to damage anything. First see individual, like, normal thing, then try to apply Laplacian correction and try to see how is it working. If it improves, then there must be something happening in the data. Why am I saying apply and see? Because you cannot actually look at million records, what is happening there. And contingency tables also you cannot look at, because there in a given categorical column there may be many combinations there, right? Got it?
Yes, sir.
So this is Laplacian correction, and we are going to in NLP language models, we are going to magnify this Laplacian correction into a little more. And this probability is the basis, and if you understand this or you remember this, that's enough. You don't go into probability too much. This is enough. Okay, I'll cover all kinds of things in language models and all. So I think you got a gist of how the this naive algorithm is working and what is Laplacian correction also. So there are these are the things I am actually talking about. Pros. It is relatively easy algorithm to build and understand on a huge volume of data. You can actually do it by calculating these. The what you call it as the scikit-learn implementation. I don't know whether it can handle or not. But if you want, right, you can actually do it on huge volume of data also. If you can manually create these frequency tables and likelihood tables, so you can actually do it. This is not a big algorithm to implement. Okay, it is faster to predict classes using the algorithm than the many other algorithms, because it is just a simple probability calculation, right? And then it can be easily trained using small data sets. Right? Maybe big data sets also we can calculate, but maybe we need to do groundwork. We need to create a database of all these contingencies, likelihood tables and the frequency tables, and using them we can actually implement it. I never did it, but we can. It's not a too powerful algorithm. No need to struggle to implement it, because we have other algorithms which can help us in many other ways. So cons. Zero conditional probability problem, we call it as this one. Right? This is zero. So we are going to get zero if that is overcast. That is called as zero conditional probability problem. The problem is known as zero conditional probability problem, and this is a problem because it wipes out all the information in other probabilities too, right? Because of 1, 0, all the other probabilities are also getting 0. So this can be corrected using Laplacian correction. That we have seen it. Another disadvantage is very strong assumption of independence. Class frequency that it makes, right? It need to implement such as. Yeah, it is near to impossible, right? I am saying near to impossible because there will not be any data set with independence, that much independence. But if it is decent independence, right, you can use it. That's where on the text problems, naive Bayes is taken as an example, because when you create a count vectorizer, the data is actually a little bit of independent. The input space is a little independent. Not that independent, but it is little independent. Okay, and the next thing is there are 3 variants here. Here we used Bernoulli naive Bayes. Okay, and in the scikit-learn there are 3 implementations: Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. Here I used Bernoulli naive Bayes because the data mostly is zeros and ones. What is Bernoulli trial? What is Bernoulli trial? When your experiment has got only 2 outcomes, then you call that experiment as Bernoulli trial, right? You throw a coin, you get head or tail, right? So those kinds of problems are experiments are called Bernoulli trials. So here Bernoulli naive Bayes we are saying because the data is all having zeros and ones. Okay, and there is a multinomial naive Bayes, right? When I say multinomial, you throw a die, you get 6 numbers, right? The outcomes are uh, discrete and discrete, countable, right? But not greater than 2, right? That is multinomial. Generally, the count vectorizer you should be applying multinomial naive Bayes. In this particular data set, I applied Bernoulli because zeros and ones are coming. Generally, there will be numbers, right? If there are numbers in the data, then you should be using multinomial, integers in the data. Gaussian naive Bayes, when your data is actually real numbers, right? Or the data is satisfying normal distribution, each column is actually normally distributed, then you should be using Gaussian naive Bayes, right? We are actually calculating probability of individual column, right? Given the class, individual column given the class. If each column is satisfying Gaussian normal distribution, then you should be using Gaussian naive Bayes algorithm. Got it? For real numbers, right? Will you get real numbers in the data? Yes. For a text data set, you will get real numbers when you apply TF-IDF algorithm rather than count vectorizer or the bag of words. I'll explain what is TF-IDF. We need to understand information retrieval concepts, which are very strongly related to NLP. And in real time, there will be many problems that are overlapping between information retrieval and web mining. We call it as data mining, right? Web mining and the NLP. I'll explain that also. Maybe next week, by end of the week, right? We'll cover all these concepts. Okay, with examples, I'll cover. So, any questions? That's it on the introduction to natural language processing. I took around 3 days or 4 days, and I'm saying introduction. Yes, it is. It is introduction only. We have many things to cover in NLP. Any questions?
Sir, here actually we have taken the binary classifier.
Yes, sir.
So how will the probabilities work with multi-class?
We'll calculate multiple probabilities there. Here, right? Given yes, no, we calculated, right? We'll have another column here, right? If you have 10 classes, right, there will be 10 columns.
Okay. So
And 10 probabilities, likelihood tables, and then there will be more terms here, like more probability. Probability of yes given, no given, right? All right given, like that. There will be more probability. Whichever probability is high, the record belongs to that class.
yes, yeah. Got it.
Yeah, these algorithms are not big, but they are confusing. Right? When we dismantle it and see clearly, the confusion reduces. Right? Tree-based algorithm is also not a big algorithm, but it is confusing. How the splitting happens, how the tree, the random forest algorithm actually resolve overfitting. These are all the things, and these are all interview questions. Whatever I am explaining right now, all are interview questions, and this terminology is what they play with. Even though they don't know anything, they play with this terminology. Okay, so let me stop recording.